So what I was saying is that the motivation came a couple of years ago when we started to work on it with Zach Kilpatrick, and he was in contact with Shiwan Shu at Georgetown University, where there was a couple of experiments about wave initiation. So what I would call evoked waves coming from a stimulus. So we're talking about your visual fields. So these experiments were done in rats, and I'm just showing some recording of the rat visual cortex when it's receives a stimulation. So it's a black dot on the screen, and the type of waves that we have considered, or where we wanted to have some analysis, are either evoked waves, so which are directly elicited from a stimulus, or other type of ways that you can get spontaneously. You can get, for example, during your sleep, you can get this spontaneous wave, which shares very similar patterns to the wave that you would get from an evoked by a stimulus. So the type of models that we had worked with at the beginnings are the traditional neural field equations. Yesterday, we had plenty of talks about it. So in the first case, say for spontaneous waves, I'm just considering the neural field equation without external inputs, and what drives the dynamics, obviously, is the initial condition. And in the second case, which I will not have time to talk about it today, is the evoked case. And in that case, you start with, say, zero initial condition, flat state, rest state. But this time you add some external drive to the equation. So here it's for some amount of time you show some stimulus. So the question is, what can you say about the long-time dynamics of the solution of these two types of problems? So obviously there are various references associated to it. And what I was mentioning yesterday, maybe before I got stopped, is that we got also to talk with the group of Frédéric Chavannes and Alain Destex, and they have lots of work related to this type of question. They have also some models way more difficult than the one that I'm presenting here, and maybe I will have time to discuss about it at the very end. So as I said, I will be basically talking about case one. About case one, what is interesting, or what makes the analysis interesting, is the type, obviously, of initial condition that we'll be considering, the type of internal dynamics that we're considering, and I would say that the structure of the network, meaning the type of connectivity kernel that I'm picking, I'm just getting here a very natural setup where throughout K, the interaction kernel will be assumed to be symmetric positive, bounded, integrable, and I have some normalization condition where its mass is equal to 1, which just means that if you look at the homogeneous equation without space, it's just given by the ODE, which is u prime is equal to minus u plus s of u. And I'm assuming a second moment, and it will be somehow important, or it will be easier to compare with what I will be saying later on a different model. So the type of initial condition that I'm considering here are families of initial conditions. There will always be a small parameter L if you want. So the easiest case, or the one that is simple, or that I will be mainly focusing on, is the case, for example, of where phi is just the characteristic function of some interval minus LL. So this will be about the initial condition, but I will be coming back to it. And what is more importantly is that the dynamics, the internal dynamics of the system, I'm assuming that it's of bistable type. So what I mean by bistable type, I mean that there exists three homogeneous equilibria that I will denote 0, 1, and kappa. 0 and 1 will be the stable one, and kappa will be the intermediate one that is unstable. So a little bit as in the setting described by Mathieu in his talk yesterday about this bistable or excitable type dynamics. And I have a further assumption here that the integral between 0 and 1 of f is positive. This just means that 1 is more stable somehow than 0. And the typical question that we wanted to address and understand is the following, is depending on the initial condition, can you decide what is the long-time dynamics of the solution? So it turns out that in that case, the long-time dynamics is kind of boring. You have basically, roughly speaking, two types of possibilities, at least under the assumptions that we're making and for the type of initial conditions that we have. It's either you will converge to 0 uniformly, or locally uniformly, you will converge to the stationary state 1. So this is kind of a generic situation that will happen for the type of initial condition that we get. So there are obviously some configuration where just by a simple comparison principle, you can already see that what will go is when you have an initial condition that is squeezed between two stationary solutions, say that your initial condition is in between 0 and kappa, you will converge to 0, and on the other side, you will converge to 1. But what we want is to have initial conditions that are above threshold. And in that case, it's more difficult to decide what will be the long-time dynamics. Does the solution will go extinct, or does it propagate and converge locally uniformly to the upstate? We have also investigated more, say, initial condition that have say multiple active regions, so multiple regions where they're above the threshold. And in that case, the long-time dynamics falls only in two types. Either you converge to 0 or to 1, but the transient dynamics is more difficult to understand. And I will not be talking about this last case, and I will be mainly focusing on case B, which is the simplest one. And actually, this allows me to explain this type of problems in a different setup, because this type of question is very natural and has been investigated in the reaction diffusion community for a long time now. So for me, the prototypical equation in that case would be the reaction diffusion equation, where the diffusion process is just a Laplacian. You get the reaction term. It's the same f of u that is bistable. And as I said, just to simplify a little bit, we take as an initial condition just the characteristic function of the interval minus L. And what you want to understand is what is the long-time dynamics of the solution when you vary the size of the initial condition. So the type of f of u that we have in mind, if you want, the prototypical example for a smooth f of u would be just a cubic nonlinearity for where the intermediate state here A was the kappa just before. And famous results, so that appeared in different papers, in a series of papers, is that for the solution of the above Cauchy problem, you can find a critical value, L star, strictly positive, where you get a kind of a dichotomy in the long-time dynamics. So if L is below this critical value, then you go extinct and you converge uniformly on R to 0. If you're above that threshold, then you converge to 1 uniformly locally. And at the critical value, what the dynamics is a little bit is different. And actually what you get is that, so we call it stagnation with Zach, but you converge to the unique, even positive solution, stationary solution that is non-trivial for associated to the stationary problem of the PD. And actually this solution U, sometimes it is called a ground state, depending on your community, It's totally unstable for the dynamics. It's very easy to see if you just linearize your equation around this ground state, it has to have an unstable eigenvalue. So it's really this ground state serves as a separatrix for the dynamics. It's an unstable configuration, if you want, and this is the typical result. So it first appeared in the work of Canel in the 60s. Then you get some results, partial results by Aronson and Weinberger, but also Faye, MacLeod, maybe 2 years after. And the first proof, rigorous proof in that setting is due to Zlatos at the beginning of 2000, and then it got extended by various others, and there are many more references associated to it. And it has been extended to different type of initial conditions, also extended in multi-dimensional setting, and not only on the real line, but I will stick to that case here. So what we did with Zach at the first place was to come back to this to the neural field equation. So we made a huge simplification, is to replace at the first place the nonlinearity, which is supposed to be smooth and of sigmoid type. We replace it by our favorite Heaviside function to get insight on what you would get in that case. So obviously you need to be very careful about what you mean by the Cauchy problem and existence of solution. Existence is fine, but uniqueness, you can be in trouble if your initial conditions are not well suited. So this is why I write it a main result here, because some part of the analysis are a bit formal, and I will come back to more rigorous results later. But essentially what we found is that there is also a threshold phenomena, a short threshold phenomena in that case, for initial conditions that would be smooth and unimodal with only one active region. By one active region, what I mean is that there is one, only on some given interval, the solution is above the threshold. And we can precisely characterize the critical value for the size of the initial condition when you either converge to 0 or converge to 1. And this is related to the threshold of the nonlinearity kappa and the connection, the kernel K. And also at the critical value, we also get the convergence toward a stationary solution. So in the case of the Heaviside function, it's more easy to characterize stationary solution, and we can do it correctly. So why did I say that the analysis is formal? It's just the type of proof that we're using. We're using an interface dynamics approach, and we have to be extremely careful about uniqueness of the solution. And I refer to that very nice paper by Curie and Stannat, where they talk about these issues of non-uniqueness in neural field with Heaviside function. But anyway, here, if you use this interface dynamics approach and you characterize the active region, you can get a closed form formula for the equation describing the boundary of the active region. And if you only stick to the first equation, you already see why we get this dichotomy in the equation just based on the initial condition, and if you're below or above a threshold. So this is, I would say, what we did with DAC on the formal analysis, and now I want to present some results that I've been obtaining on a different context, but with smooth non-linearities. And unfortunately, I cannot be yet as precise as in the Heaviside case or as what has been done for traditional local reaction diffusion equation. So coming back to the neural field equation, but this time I'm not assuming that the nonlinearity S is the Heaviside step function, but it's any smooth non-decreasing function, sigmoidal-like, such that f of u is bistable under the terminology that I've given before. So by smoothness here, in some parts of the proof, at least at least C2. Well, so this is the assumption that I'm making here. So in that case, you can define very properly. There exists the uniqueness is restored, and here I'm working in L1 and L infinity for the notion of solution in the sense of integrated solution, and I'm sticking with the characteristic function of the interval minus LL. So what we can get, not too difficult to get actually, is that you always get extinction if L0, I mean L is sufficiently small. And so we can define the largest value for which extension can happen. And just because it's interesting to see how this type of proof works, I just had one slide to explain it. Essentially here, what we're doing is just using on and on comparison principle and constructing either a super solution or sub solution that are appropriate for the problem. And so, for example, here to get extinction, what you want to do is to construct a super solution for which you know that they will go extinct asymptotically in time. So here, it's a very naive approach. Is your non-linearity, you can, because of the property that S at 0 is 0, it is smooth, can always find some constant S naught larger than 1 so that you can bound your non-linearity by just a linear function. And so instead of working with the nonlinear problem, you can work with this problem, which will serve as a super, this will create super solution for your problem that will bound by above your solution. And so now it's very easy to conclude because you can just see that you can control the L1 norm of the solution here. This gives you some indication, and then you can just directly solve this problem you get by using a UML formula and just do some Young inequality in the convolution term. And you see that the solution there are always bounded by this quantity. And then you get some time for which one part is going to be less than the threshold over 2, the other part, then you will get the L0 for which it will also be less than the threshold over 2. And from there, you can have that for all time larger than this value, any L below that critical value, the solution will always be below the threshold. And from there, you can, use another comparison principle to conclude that the long-term dynamics of the solution has to be 0. They have to converge uniformly to 0. So this is really the type of argument that you use in that case, very elementary, but robust somehow. Obviously, the drawback here is that you cannot get a very fine and precise characterization of the size L0, the sharp, if you want, the best constant here. But I will come back to it later. So for propagation, in the sense that what you expect is that if your initial condition has its support that is really large, then you expect to have convergence to 1 locally uniformly. So for the proof, it's a more delicate proof because you need to construct that case sub-solutions. It's usually more difficult to construct sub-solutions. And for the type of proof that I'm using, I need stronger assumptions on the kernel. This is related to the fact that I can say it here maybe in the construction. What I'm doing is that I'm taking 2 fronts. So fronts, they're solutions, traveling wave solution to the neural field equation. So they're known to exist since the pioneer work of Hermantraut and MacLeod. And for these fronts, I need to have some information on their decay at infinity. And it's easier if they decay at some exponential rates. And this, you can ensure it if you have that the connectivity kernel also is exponentially localized. So this is why I need to introduce this technical assumption that I think should be relaxed somehow. But anyway, in that case, you can you obtain local uniform convergence by getting sub-solutions that are just the concatenation of two traveling fronts, and you can squeeze them below any solution. So the type of subsolution is reminiscent of the work by Faye and MacLeod, but here in that case, the non-local structure of the equation makes it very difficult to prove that you can actually use this type of solution as sub-solutions. So obviously, just a partial summary, and I guess that I'm already running late, is that what you can get for these smooth nonlinearities, extinction for small initial condition, not too difficult to get, propagation for large initial condition, so at the moment under some technical assumption, extract technical assumption on the kernel. By construction, we get that the largest value for extension and the smallest value for propagation, one is below the other one. So the conjecture at the moment, which we think it should be like the local case for reaction diffusion equation, or when we assume that the nonlinearity with the Heaviside function is that there should be a sharp threshold, meaning that these two values should be equal. This is what I get in my numerics, but at the moment I'm not yet proving the equality. It's very tricky, and just because most of the arguments that I know from either the Zlatos or Du and Matano, they rely really on techniques that do not pass when you get non-local terms into the equation. And what also we conjecture at the moment is that at this critical value, you should converge to the unique stationary solution of the neural field. But proving uniqueness and studying the stationary solution of this problem is also difficult if you want to be as general as possible. In some specific cases, we can get some information, but in full generality, it's still difficult. And obviously, the choice of the initial condition here is just for illustration purposes, but we can handle more general initial condition. And I just wanted to have one comment about the other type of equation that you might want to consider, or that you might have already seen. So I'm writing down here the Nagumo's equation, so which is usually used to describe, say, spatial evolution in. I mean, you could use it as a model to describe visual areas, for example. So the main difference here is that the diffusion process is non-local, but the reaction process here is local. And I'm asking exactly the same question as, what can you say about the long-time dynamics in that case, where I've just replaced here with a non-local diffusion. And it turns out that in that case, there is something that happens that is really intrinsic to this equation, is that what I call stagnation is convergence to a stationary ground state solution of the problem. In the other cases, it would happen only at one given value of the initial condition for one special L, and the ground state solution was always unstable. It turns out that in that case, it could happen for values of L on interval. And this is due to the fact that for this type of equation, stationary solution can be discontinuous and stable for the dynamics. And obviously, this poses some questions, and it's interesting to see that in that case, the long-term dynamics could be really different. So I have another cartoon here. So on the left-hand side, it's just an illustration of the type of stationary solution that you get. So you get, they're symmetric, you get two discontinuity points. And on the right here, I have some diagram that I've computed numerically, so extensive numerical simulation for any D. So D would be the diffusion coefficient. A would be the unstable state when I'm picking this specific nonlinearity. I'm using a given kernel, so here the exponential function. And what you see is that this diagram, so where I represented either propagation, extinction, or stagnation. And so if you want the transition between extinction and propagation with only one value, here is the usual setup that you get for local equation or for traditional neural fields. But in that case, you get for small values of the diffusion coefficient, different possible behaviors. So for example, here, if you're in that region, I fix D and I increase L. So I have first extinction, then for some time, for some region in L, stagnation, meaning that I will converge to a stationary solution. I don't have either extinction or propagation, and then I get propagation. But if the coefficient diffusion is even smaller, then I don't have anything. I just have stagnation. I fix an initial condition and the support will not move and I will just converge to some ground state. So it's very interesting and very different features from the equation, although we could think that the equation are very similar somehow. I think that I will stop here at some slide to explain how you can construct such a discontinuous ground state, but I'm already running late. What I can just mention is that by studying these discontinuous ground states, they intrinsically appear as one parameter families, and this allows you to construct either sub or super solution, which helps you get either non-extinction results or non-propagation results that they serve, if you want, as barrier for your solution, and you can squeeze such stationary ground state solution below your solution by still using comparison principle arguments. So my overall summary is that you can see this initial question about spontaneous wave initiation. You can link it, or it appears also very naturally in this type of questions for reaction diffusion equation for the threshold phenomena. There are lots of open problems. Obviously, comparison principle techniques are a key tool in the analysis. The structure of the equation really matters, and hopefully I've convinced you that if you take a different equation, so say Nagumo's equation with non-local diffusion, you can get a very different feature for the long-time dynamics. The questions of deriving quantitative estimates on the threshold is a very, very difficult question. So we were very lucky with Zach to get an exact formula somehow in the case of the Heaviside function, but this never happens. And actually deriving some more quantitative estimates is very difficult. We got some work done with Mathieu Alfaro and Arnaud Ducrot in the local case, but still there are lots of very interesting questions that needs to be solved. I've definitely not talked at all about evoked wave, but they can really be studied similarly. As I said, the analysis is slightly more intricate because the transient dynamic is more involved, but the long-time asymptotic is the same. Either you go extinct or you have propagation. And with Zach, more interestingly, is that we're also studying the interaction of waves. So, for example, if you have a stimulus that are where you stimulate a different position in space and a different position in time, at different time, and you see this would generate, for example, two waves and how they interact, eventually merge, fuse, or get suppressed one by the other one. And we'll also have some ongoing discussion with Frédéric Chavannes about comparing it to data. And thank you for your attention. And sorry if I was just too long.
Thank you, Grégory, for the end of this very nice talk. Are there questions in the Zoom room? No. And here, Olivier. Thank you.
Thank you, Greg, for your very nice presentation. I have a somehow, well, not naive, but it's an old question. You have a comparison between heaviside function and smooth sigmoidal functions. You have built solutions in both cases. And I've always wondered what happened when you deform smoothly the sigmoid to the heaviside. Do bad things happen or not?
So, okay. So what I would say, define what you mean by bad things.
No, maybe.
So do you? So you?
Is it continuous also on the solutions?
Yeah. So okay, it's a good question.
We still don't know.
At the limit, I know that at the limit, so when you're the heaviside, you have issues, but along the way, I'm not so sure that you would get issues. I would have to think about it more carefully about what you, for example, I think that, you may lose uniqueness, but I'm guessing you only lose it really at the limits, not, I don't know. I'm sorry, I'm not super, I'm not answering very well your question. I'm sorry, Olivier.
Okay, thank you.
There are some work where people have done the other way around rigorously. Is like you start from the heavy side and you say that you deform the heavy side to the continuous case. So, for example, you have a results with the heavy side, and you deduce some results for the sigmoidal function when you take some limits. For example, for construction of traveling waves, I've seen that, but the other way around, I would not be so sure. Willem, you have a question?
Yeah, probably I can. Yeah, I have a question and probably a comment to the question by Olivier.
Yeah.
So we have a comparison principle concerning the firing rate. So if you take two firing rates, discontinuous or not, and they are the difference is one is lower or equal to the other one, then you have a comparison of the solutions, and that's actually so you can then get, for example, Perron-Frobenius type approximation, Perron solutions. So you can just iterate and see how the solutions of the continuous firing rate converge to monotone, monotone increasing or decreasing to the solutions of the corresponding heaviside function. But in the limit, they can become discontinuous. So you have, let's say, probably the equicontinuity becomes worse and worse.
Mm-hmm.
There's a lot you can do about that. So it was mentioned in well, it's an advertisement, but okay. So that was mentioned in this paper by Krüger and myself. So where we use actually this Perron method to look also at the neural field equation with discontinuous firing rate, and also convergence of the wave equation for the neural field equation with continuous to discontinuous, and so on and so on.
But one point that I got from your paper for your analysis,
yes.
that for the heaviside function, the initial condition really matters, and
yes,
in a sense, so the case that I have in mind is that if you're say your initial condition is monotone and say smooth, for example, then uniqueness is restored of your solution, and you will preserve this type of properties. But we can easily think about a nasty situation where your initial condition will somehow oscillate near the threshold on a very, very large domain, and then everything boils down. I mean, it's really an issue on how much you can cross or be close to the threshold that really matters.
Yes.
So, but I could not make your argument work for, say, the type of initial condition that I was presenting. So say you're smooth and you have only two crossings that are non-degenerate.
I think this is a misunderstanding here.
Okay.
So we are talking about two different issues.
Totally. I totally agree. I switched to the Cauchy problem.
Yeah. Okay.
Yeah.
So once again, so probably I would make this point because it's important. So one thing is you consider the firing rate as a parameter, and as a parameter, the solution is a monotone solution in this parameter. So if f is increasing everywhere, then also the solution of the wave equation, no matter what the initial condition is. So you just take the mild formulation of the neural field equation. You just convolute with the kernel, blah, 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 and all these kind of things. And the other thing you are referring to is, of course, clear. So this is this problem of, in the discontinuous case, of what to do with the solution on the level set of the threshold. If that is no longer, so we identified an so-called absolute. So besides the classical transversality condition, which is known in hysteresis of stochastic reaction diffusion system, identified this absolute continuity condition. So if the level set of the solution on the threshold is in a neighborhood continuous with respect to a Lebesgue measure, then you are done. So that's a slight generalization of then you get uniqueness. It's a slight generalization of the transversality condition. But sorry, that's too much for the discussion. But one last question to Grégory. Isn't it so that if you have this exponential kernel, then you can transform your neural field equation into the into reaction diffusion system? And at least in that case, you could come up with precise values for L.
So
L star, sorry, for L star.
I would say yes and no.
Okay.
It's so yes to the first part of the question, and partially yes to the second part of your question. So yes, you can transform. So for example, maybe I had a slide about it, but I was just not on time. So here, maybe on that slide, it's so what I'm doing is that. So this is for the non-local Nagumo's equation, but reuse it if you want. So with this exponential kernel, you can recast it as a different, just a higher order dynamical system. So in that case, it's just second order. And what we're doing is just inverting so I've denoted V, it's just the convolution of the kernel with U being the actual solution. And then this is one part of your question is that yes, for a stationary solution, you can do this transformation and you're back into I would say, a familiar setting. What's happening in that case is that the nonlinearity, the new nonlinearity that you get does not need to be all the time monotone. And we can clearly see it when D is small, or when D is really large, then you're almost near identity and you can invert it, safely. But when D is small, then you will get different, depending on your initial nonlinearity, you will get different regions of monotony. And so what you want to do is that you can only invert your system on the region where your nonlinearity is monotone. So here I've assumed, for example, it has 3 regions of monotonicity. And so you will be able to invert only on that branch and that branch. And the way you construct stationary solution is that you do favorite gluing phase portrait analysis. You superimpose two phase portraits. So this is one part of your question. The second part is, does the exponential kernel allows you to get closed form formula for any type of threshold? The answer is yes and no. So I had one. So it's kind of miraculous in that case, is that, so you see I have several boundaries between either extinction, propagation, or stagnation.
Mm.
So what I can get a closed form formula and explain what happens is why you get what happens here at this spatial value where that curve seems to meet that one.
Mm.
So can prove that it happens here. I can prove that you start to get extension that kicks off at that point. And what we could do is to derive an analytical formula for the dark blue curve, because we were using the exponential kernel, and it's given by if you want the ground state, it has a discontinuity. It's discontinuous at 2 points. And you take the largest possible ground state. By largest, I would need to define it, but and you take its discontinuity point, and this is precisely that boundary. And so we can get it and get analytical formula in that case because we use the exponential kernel. And so to get this full picture, I also relied a lot on the fact that I picked the cubic number.
Greg,
it's really a mixture of
Greg,
a lot of,
please.
Yes.
I think we have to
Thank you.
stop the discussion.
Sorry.
Thank you very much. Thank you, Wilhelm, for this interesting question. We thank again Greg for his talk.